We are ready. Okay.
Hello, good afternoon.
Welcome.
Are you able to hear me ours? Oh. Reza, have a seat.
How are you?
I'm good.
Great.
Thank you. Feel not so great.
Not great.
Okay, good afternoon, everyone. Happy New Year. Still we are in January, and we're back to work. And today we have Mohammed to give us the completion seminar for his research for almost 3 years, not yet. Mohammed, so you have about 6 minutes. You tell us your research so far, and then we will ask you questions, and then we will this report for you, and then that's the process. Okay,
Sure.
please.
I thought I had about 40.
Around.
Around,
You
okay.
can
Okay.
have more than 7 minutes.
I think I might need to.
Yeah.
Thank you. Good morning, everyone, or good afternoon. We have a lot of people, so thank you all for coming. Thank you for the panel for coming as well. My thesis title is Randomized Motion and Parameterization Motion Planning for Autonomous Cars. Our supervisors are Dr. Milan and Professor Reza. Thank you for coming. The aim of this presentation is to highlight current gaps in the literature, identify my research progress, my writing progress, and my research outcomes as well. I want to start motivating my research by some statistics on transportation. Obviously, cars are the most popular mode of transportation, of personal transportation, in terms of the daily time spent in cars and the daily distance traveled by cars. Unfortunately, around 1 million people lose their lives in fatal car accidents around the world. The majority of these accidents can be linked to unintended lane departure caused by human error. So I guess the motivation behind autonomous cars is to remove that human error from the driving. Before I go ahead, I just want to explain what autonomous behavior is. There is still no strict definition of what autonomy is, but we'll use the cloud definition, 2002. He divides sort of 3 behaviors, or defines 3 behaviors: automated behavior, autonomous behavior, and intelligent behavior. What we're looking at is autonomous behavior which independently executes tasks. For example, for a car driving from point A to point B without any human intervention, but it doesn't define what these points are, which an intelligent system would do. The behavior of autonomous cars can be described using the sense plan cycle, sense plan act cycle. In this sense, we use a combination of different sensors, obviously internal and external, to create a model of the environment and the vehicle within it. Based on that belief or that model, we want to plan, define some goals and plan a set of actions to execute these goals. And then finally, using some control laws or feedback control, we'll be able to execute these actions. And this is sort of an iterative process. Planning has been identified as a critical capability for autonomous cars. Our research, this is a paper by Ivan Guzman, and our research is somewhere between route planning and mission planning. So So route planning is what your navigational system does, but it doesn't define the actions, or not commercially, for what the car will be doing. There's obviously different planning definitions for different fields. I'll be relying on Laval's book, Planning Algorithms, for the definitions. The scope of the research is motion planning. So we attempt to drive the car from point A to point B. We consider the constraints of the car, but we also consider the environmental limitations such as obstacles and other cars. There are several challenges to autonomous cars and using autonomous cars on roads. The main challenges for motion planning are identified as safety and passenger comfort. Safety for autonomous cars has been pioneered by Frischard since 2007. He defined a specific criteria, which is minimizing the decision time for a motion planner as a criteria for motion safety. And for passenger comfort, Diels since 2014 has been pioneering that research, and he proposed altering the motion profile of the vehicle to minimize the disturbance on the passenger and improve the passenger comfort. This is the classic sort of breakdown or categorization of motion planners. In the literature, I just added a sampling-based planner, because that's a relatively new field. We evaluated all the categories for these planners based on the criteria by Diels and by Frischard. We identified sampling-based planning as a potential approach or a potential solution because it generates paths quite efficiently, and with specific parameters we can also improve the quality of the resulting paths and trajectories. Several researchers have looked into this field, which is combining some sort of curves or fitting some sort of curves with path planning. The relevant work is from University of Sydney by Kwon from 2010 to 2014, and I'll be using that as a baseline for all the experiments. So there is a clear need to improving motion planning for passenger vehicles. To answer that question, there's obviously several questions that we need to answer. The first question is, what are the challenges for implementing existing path planning algorithms for autonomous vehicles, which we've answered in the literature review. The second question is, how can parametric splines be used to model the vehicle's motion? What is the effect of that continuity on the vehicle in terms of the resulting disturbances and the tracking performance? And what is the effect of using that solution within a randomized plan? Identified planning algorithms, which are the randomized motion planners. Obviously, there's a few objectives to answer this. Identifying a suitable planning expression and framework, formulating parametrically continuous paths for the passenger vehicle, investigating those effects, identifying a suitable algorithm or approach to integrate those results for randomized motion planning, and then benchmarking them against the state-of-the-art algorithms. This presentation will be divided into subsections. Each of them is answering the research question. First one is a literature review. Second one is, which we've done. The second one is mathematically formulating the paths. And then from these outcomes, we'll be first evaluating those results based on the identified criteria, and then integrating those results in question 4 within a motion planner and benchmarking that motion planner based on the literature review. So as I mentioned before, there's some theoretical analysis in the planners themselves, analytical and mathematical analysis to develop the path, software tools to simulate and benchmark motion planners and the paths, and then there are experiments to validate the effects of these paths using an experimental vehicle. So research question number 1, as I mentioned before, has been answered in the literature review. We've published 2 papers on sampling-based motion planning and ride comfort or passenger comfort in autonomous cars. So we'll move on to question number 2, where we attempt to model the path of the vehicle. So this is the vehicle that we're considering, front wheel steered vehicle, 6 degrees of freedom. We're interested in the planar motion of the vehicle, so in the X and Y planes. It's traditionally described using the bicycle model, in which the configuration or the state of the vehicle is described using X, Y, and theta, which is the heading. And there are 2 controls for that vehicle, the forward velocity and the steering angle. The steering angle is limited, therefore it limits the curvature of the path that can be followed. And in this section, we attempt to limit the curvature of the path to match the curvature of the vehicle as well. So there are several methods to describe the path of the vehicles, combining circular arcs, orthoids, polynomials, parametric splines, and we've decided to go ahead with parametric splines based on a comparative analysis that we've done, and based on our ability to generate continuous paths as well. There are different methods assessing composite curves or joining 2 curves. Geometric classes have been defined by Barsky and DeRose, in which they look at the intersection between 2 curves to assess the quality of combining those 2 paths. So we'll be evaluating our work compared to other methods and evaluating the sort of the class of the curve based on that approach. For example, this is the Dubin's path, which joins a straight line with a circular arc, and you can tell the discontinuity in it's sort of not G2 continuous, because the curvature for the straight line is obviously 0, and then it jumps to the circular arc, which has a constant curvature, and then it goes back to the straight line. So it is discontinuous.
You're doing great. Just a little bit.
Sorry.
IT guy is not here. Can you try to move this picture up?
I have
page number.
I have no access.
You cannot move it on your screen.
No,
you
it's
okay.
not me at all.
That's okay.
Sorry.
That's okay.
We're
Please go on.
We're at 19, so.
No.
But it's in the printed
Okay.
version. Yeah. So moving on, the objectives of this segment is to nominate an appropriate path, the generation method, generate parametrically continuous curves or paths, model the curvature of the path, and bound the curvature to match the curvature of the vehicle, and then generate boundary value solutions, which I'll explain time. So we used cubic B-splines. They were created by Schoenberg in 1946 because of their local support property and independence of the degree of curve from the number of control points. So in this example, we have 1, 2, 3, 4, 5, 6 control points, but the order of the curve is independent from the number of control points, and we use the de Boer recursive formula to generate the path equation itself. So I have detailed the analysis of all the different methods in my thesis. What we're using is a cubic B-spline curve. It's clamped, so it interpolates the first and last point, and we've added midpoints between the curves to improve the sort of the interpolation and minimize the errors. At this stage, we're still just hitting a curve within the control points. So this is an example of a multi-segment path. So there's about 15 control points in here. You can see that the curvature is continuous. First order, second order are continuous because it's a cubic path. The highest continuity is C2. When we look at the third order, which with respect to time would be the jerk, we have sort of discontinuous values here. To model the curvature, we divided each segment or each path into smaller segments. Because of the local support property of these splines, we are able to model each segment using the length of the segment and the angle of the segment. We generated the control points. Using the de Boer recursive formula, we were able to generate the equation for the path and then define the curvature of the path. And here we assume that each segment is identical. It is a simplified approach, so we added another parameter, which is the ratio between the two lengths of the path to be able to model. The idea is to model the curvature of the segment using the parameters of the segment. So here I'm just going to show results from both models. In here we're generating B-spline paths using different parameters, and we're evaluating the curvature using the 3-parameter model and the 2-parameter model. At the start, we notice that the 2-parameter model always results in sort of symmetric profiles because it's assuming that both sides are equal, even though the ratio is 8:1. When we move into sort of closer ratios, so when it is symmetric, the 3-parameter model generates identical results, and then it starts moving away from the center of the path in here. You can also see that based on the ratio, the 2-parameter model will either overestimate or underestimate the true value of the curvature. To be able to, what we're interested in is the peak value of the curvature to compare it to that of the vehicle itself. So there's two approaches, either solving the equations that we generated using just MATLAB solver to be able to find the maximum value or the minimum value, or the other approach that we looked at is storing the peak values in a lookup table based on the parameters that we've identified, and improves the query time significantly. So this is the mean time for about 1,000 different parameters, and it's less than 1 millisecond. We looked at the accuracy of that approach. So the actual value refers to solving the equation using MATLAB. 3-parameter are shown in blue in here, so you can't see them because they're almost identical with the red values, and the gray values are the symmetric model, and the error is less than, mean error is less than a millimeter, which is appropriate because we're looking at tens of meters. So it is appropriate. Having defined the path and modeled the curvature, the next step is to bound the curvature to match that of the vehicle. So we generated 3 methods. The first method is adding a segment to the path. So for example, if we look at part A in here, if the curvature of that segment exceeds that of the vehicle, we add an additional segment to minimize the curvature or to bound the curvature. The next approach is increasing the segment angle. So you can see that the curvature decreases when we increase the segment angle. And the third approach is adding a segment within the existing segment. So instead of having 5 control points, we have 2 segments in here, and you can tell that there's 2 segments based on the peak curvatures. We evaluated them, but keep in mind that we're still not considering any obstacles. This is just minimizing the curvature to match that of the vehicle. This is the original path shown in gray, and these are the 3 solutions. They all bound the curvature, and they all generate continuous curvatures, but we still haven't considered any of the obstacles. The final solution in this segment is a boundary value solution, and I'll explain why we need that solution in Reece's question number 5. But as I described earlier, we can describe the state or the configuration of the vehicle using 3 values, so x, y, and the heading. So this algorithm generates a B-spline path between any 2 configurations that we need to connect. I'll just show a video of varying configurations to show the algorithm in use. So we'll vary the initial and the final states to generate the curves between them. So here we're changing the initial heading. Here we're changing the final position, but maintaining the heading and the start position. And here we're changing both the start position and heading. So these are all generated in real time. We're not plotting existing results. changing the final position, and varying the start and final values as well. So up to this stage, what we've done is we've generated or developed solutions to generate paths. We haven't evaluated these paths, and we haven't still considered any obstacles. It's still path planning problem. In this segment, what we want to do is validate the parametric continuity, evaluate these effects on the resulting disturbances and on the path tracking performance. We'll be doing that using standard experiments, so Vasquez-de-Rose and Gonzalez's method to evaluate path tracking and Roth and Batavia, resulting accelerations, and Roth and Batavia to evaluate the tracking performance. We replicated the experiments by Ho and Chan in 2014 and Zhu in 2011. In all the experiments, we were able to generate lower curvatures with higher class curves. Similarly, in here, I don't have the length of the path in here because it wasn't defined in their paper. So I don't have the results right now. I'm just going to show one example. As I mentioned before, this is the research done by the University of Sydney. So we generated two paths for a similar experiment or benchmark. And these are the resulting trajectories that we get, or curvatures that we get. You can see the effect of using a single curve without creating composites. There's no, they're all continuous, they're all sort of differential with respect to the path length parameter. And here you can see the effect of combining a straight line with another curve, and then another curve, and then a straight line as well. And it's evident in the second order as well. To evaluate the tracking performance and the resulting accelerations, we conducted 3 case studies. We generated paths using 3 different algorithms and at 3 different velocities, and we used a standard path tracking controller. This is the first case study. It's a step change path. It's quite standard by Roth and Batavia. We generated a lane change maneuver and a double lane change maneuver, and you can sort of see the effect of the continuity on even the shape of the path. This is a single curve. You can see visually the effect of combining different curves, and in here, straight line, circular arc combinations as well. Continuity decreases. We decided to use the pure pursuit tracker because it's the most commonly used tracker. It's sort of the baseline for tracking algorithms, so it's quite suitable. I think it's a massive thesis by Snyder, showed that it's robust path discontinuity, which is what we're assessing, and external disturbances as well. The values that we'll be measuring is the tracking error, the control effort, and the weight sum of the RMS acceleration, as shown by the results. So this is an example of what we expect to see. These are 3 resulting paths after we use the controller, shown as the solid blue lines. The controller maintains a fixed velocity and varying steering signal. You can see the effect of discontinuity. As the discontinuity increases, there's slight oscillation in the signal that we're getting from the controller. And here, because it jumps from a straight line to the sort of a step change, the controller generates sort of an oscillating signal. I'm just going to show an animation of the paths to show the scale of the experiment. So this is a vehicle with a wheelbase of 2 meters. The blue path is the reference data set that we generated, and the red path is the result from the pure pursuit controller. This is a double lane change. A lane change and double lane change. So the results. Our results are shown. This is the tracking error for the different experiments, so step change, lane change, and double lane change. Our results are shown in blue, so the tracking error is reduced for the pure pursuit controller. In the lane change, I also used a sinusoid lane change, which is the baseline, sort of standard lane change maneuver. So, and our results are also quite comparable to the baseline tracking error using the sinusoid. Similarly, for the control effort, our results are shown in blue, and we reduce the control effort, for step change, lane change, and double lane change as well. Look at the resulting accelerations. Similarly, results are shown in blue, and they are reduced for all the experiments at all speeds. We added noise to the controller to evaluate the results. And we compared it with the field experiments. So MATLAB generated the velocity and steering commands to two separate PID controllers on the vehicle. And we measured the lateral acceleration and compared it with the resulting accelerations from the actuation nodes. This is a video of the experiment. This is the step change. I reduced it for the experiment because there wasn't enough room to run it in the campus. I think this is 20 or 20. Similarly, this is lane changes. I'm just going to skip through to this part. So these are the results from both experiments. The red results are the experimental results, or what we measured from the accelerometer, and the blue results are the numerical results. You can see that there is a difference at lower speeds, and that was mostly because of the engine control unit itself. At lower speeds, the controller was oscillating because the wheels were spinning, but at higher speeds, the results were quite similar. So we've generated, up to this stage, we've generated different path solutions. We've evaluated the effect of using these paths on the path tracking performance and the resulting accelerations. And in this segment of the presentation, we'll generate a randomized planner using these solutions. We conducted a literature survey, so this is the standard motion planning or planning category that I've shown earlier. After the survey, we used RRTs because they are the most popular approach, and they can be used for motion for autonomous cars because they're single query. What we will be comparing with is best input motion planners, post-processing parameterization, and our new approach. Randomized planners are biologically inspired. The work by, I think Ben Eschel published a research show explaining how bacterial colonies grow, and it was modeled using what's called Brownian trees or diffusion limited aggregation. This approach was used by Laval to randomly generate trees and explore the free space in the environment with and without obstacles. So this is an example after 200 iterations. The algorithm is capable of capturing all the free space in the environment. The algorithm randomly selects a node in the environment, whether it's in an obstacle or if it's not in an obstacle. It finds the nearest node in that tree based on a predefined metric. And if there's no collision and if it's feasible to add a tree based on several criteria, the new tree is added, the new node is added to the tree, and that's how sort of the tree expands. So the objectives of this section is to implement state-of-the-art motion parameters or RRT-based motion parameters to be able to benchmark them all. Identify, because this is a new sort of field, identify what are the benchmarks for randomized planners, integrate our model within a planner, and then benchmark all of them. So I use Python as an environment. It's because it's just easier to develop for research and it's a bit more flexible. All the functions and the classes are used for all the planners. The only difference is the algorithm itself or the logic itself. I use all the standard modules for Python. I didn't use any libraries for the algorithm itself. And here I verify some of the parameters or the performance indices of an RMIT algorithm to make sure that our implementation is valid. So this is an RMIT that started from 0 to 0, similarly here as well, from 50 to 50, and it quickly explores the free space. So the obstacles in here are translucent. The tree is it's avoiding the trees. This is the uniform sampling process. So even though there are samples in the obstacles, they are avoided by the algorithm. And it stops as soon as it reaches the goal region. When we increase the density of the sampling towards the goal, it can speed up the planning as well. It's shown here. So increase the density and the tree sort of gets pulled towards the goal region. The other heuristic that we looked at is generating two trees from the start, 0, 0, and the finish at 100, 100, for example. And they both randomly explore the environment, and when they're connected, the solutions, we find a solution basically. Showing the samples, so there's no bias, it's purely randomized sampling. And again, we find a solution once the trees are connected. So the benchmarks were based on a recent paper by Mo. He identified 3 major benchmarks for randomized planning. We call this one Clothier, so it has randomly allocated obstacles. There are 2 reasons this is a sort of challenging for motion planners. The first reason, having a large number of obstacles slows down the collision checking procedures, and it has decoy paths as well. So ideally, you would want to find a path that's within the red path, not any of the other paths, which is challenging for any optimization-based method. This one I call narrow, because it has a narrow passage, so it has a lower probability of sampling free nodes in here. So there's 3 free nodes for the entire sort of space in here, which are shown in red, compared to all the other blue nodes. This one is called trap because it is counterintuitive for any greedy algorithm. As I showed before, when we increase the sampling density towards the goal, trees sort of pull towards the goal. And in these cases, it will not fail because it is based on a probability, but it will take significantly longer time. Also because RRTs are designed to expand outwards. These boundary nodes are all going to be in collision. I used another benchmark. This was developed by RMIT students using a LiDAR sensor. I didn't generate the map, I just used the map from their results. And finally, I replicate the 2 benchmarks by my IEEE ITS. So a lane change with varying number of obstacles and U-turn as well. Both Mo and Sukan agree that planning time is the main metric for sort of benchmarking motion planners. So we will be looking at the planning time for our algorithm. The experimental setup is quite simple. The user specifies the environment and the number of iterations that we need. For all the experiments, we ran 100 iterations. The algorithm then, once all the results are done, it generates a log file which we then visualize using MATLAB to assess the planner. I am going to skip the algorithms that we're using, but we've used 2 planners that essentially generate a path using some greedy heuristic and then attempt to fit the curve afterwards. I use the kinodynamic RT. It's not the fastest, but it is the baseline, which relies on generating discrete states, evaluating the result from each state, and then adding the state which minimizes a predefined metric. I also used reachability guided RT, which is this state-of-the-art algorithm that adds a criteria for exploration. So it evaluates a reachable set for each tree, and it will only expand if the reachable set is nearer than the original node itself to minimize the unneeded exploration. For on-node experiments, I'll use the state-of-the-art MA algorithm, which generates templates for every environment instead of using randomized search. This is the method that we designed. So as I mentioned before, most methods, or all methods, generate a path and then attempt to fit a curve within that path. And if it cannot guarantee a result because the collision checking and the path visibility is checked once the search is stopped. And here we integrate that process using our lookup table that we defined earlier within the algorithm, and we used bidirectional search and the boundary value solution to join both trees. So the animation that I was showing of the various configurations, that's used to join both trees. So this is a video of the solutions that we've, an example of the solutions that we've done. This is the plotted environment. You see that both trees are growing randomly and they're connected using a path. Similarly in here, I'll skip through because of the time. And again, we're generating two random. So all of these are B-spline curves as well. Both trees are connected and then the search is stopped. These are the histogram results from comparing our work with Yang from the University of Sydney and Kyonsu. In all the four maze benchmarks, I call them, we generated results at a much higher speed. We looked at the cumulative probability distribution function. And this basically indicates that at any time instant with 95% confidence, our algorithm has a higher probability of generating a solution. So for example, in here, at this time instant, we almost have one probability of generating a path. I didn't add the hemodynamic RT and reachability guided RT because they were just off the chart that were a lot slower than the other results. For the on-road experiments, I compared my work with the state-of-the-art MA. And for all the experiments, so lane change with 1 to 4 obstacles and a U-turn, we generated solutions at a higher, faster, just faster. Similarly, we look at the distribution of the results, and at any time instant, we have a higher probability of generating a solution. I conducted a Friedman test between all our results, and with 99.999 confidence, our results are statistically significant. So in conclusion, I presented a literature review on motion planning and identified motion safety and passenger comfort as the gaps for motion planning. I identified sampling-based planning. I've shown that spline theory is effective for deriving paths for autonomous vehicles. Using those paths, we reduced pure pursuit control effort, tracking error, and resulting accelerations. And I combined that with a bidirectional randomized planner to outperform the state-of-the-art in different benchmarks as well. Let's skip through that. So this is my research progress from my last seminar. So all the research questions were answered and published. Thesis as well. I've submitted, I think, 6 chapters. So I'm just in the process of writing the final chapter, finalizing it, and all the chapters are published. What I would like to investigate in the future is including another motion safety criteria like Freshart, which is the inevitable collision states, investigating the biological or the bio-inspired aspect of motion planners, further experimentally evaluate some of the results, such as the effect of control effort on the energy consumption and the endurance of the vehicle, evaluating the passenger comfort values on actual human subjects and the tracking error, and develop a model. I started developing a model predictive controller instead of just a proportional pure pursuit controller for path tracking. So these are my publications. Majority IEEE, robotics journals, Journal of Vibration and Control. We got hopefully one book chapter in progress, and 2 conferences, so I didn't travel as much. I've also acted as a reviewer for these journals throughout my candidature. Thank you very much. I'd like to thank, first and foremost, my supervisors, Dr. Milan, Professor Reza, the panel, for attending almost all my presentations. Thank you very much. Thanks for everyone. Didn't know I was popular. Everyone's coming through. A few people that became doctors as well. Thank you for coming. Yeah, thank you.
Okay, thank you very much for your presentation. And now we open for questions.
Sam?
No.
Yes, please.
When we do the motion planning, path planning, we consider not, right? Some case we consider optimal, right? We want the optimal path, for example, the shortest path.
Yes.
Have you considered how is it this opportunity, right? For when you do the motion planning?
Yeah. So what's the criteria that I'm considering?
For example, how do you consider your path, right? You generate is optimal.
So for the randomized planner, I'll show the algorithm itself. What I use as a heuristic when I'm generating the nearest neighbor in here, I use Euclidean metrics, so x, y, and theta, the difference between that state, to minimize the change in the heading and the distance as well between every node, and then I add the nearest node. But I looked at different parameters such as estimating the kinetic energy and sort of the resulting disturbances, but I haven't sort of fully estimated that or added that.
Okay, another question.
Sure.
Right, you choose to use a spline, parametric model. What are the limitations when you choose using this spline method?
The limitations. Well, I selected them because they're parametrically continuous. That's the main reason that I generated them or used them. The only limitation that I can think of is there's a lower bound to the number of control points that I can use. It has to be less than the order. But you taught me about splines, so what's the answer?
One more question. You do clapping, right? Using spline, right? You do clapping.
Yeah, clapping.
Yeah, you use the control point or use a node, right?
Yeah. So using the node
You use
vector.
both. Or you do not?
I use the node vector, so because it's cubic, I have four initial and 4 final knots. So it's non-uniform. But I didn't show it in the presentation, but I also add midpoints. So I assume, it wasn't shown. So I assume that what I'm getting from the motion planner or the path planner are these points. So 1, 2, 3, 4, 5. And I added midpoints to improve basically get it to be tangential at that.
It is non-uniform.
It is definitely not non-uniform. But the control points allows the path to be tangent with the control volume.
While we're on that slide,
Yeah, sure.
The selection of those midpoints, control points, you explore the sensitivity of the ratio of those lengths, or those mid. Are they
So
actually
these are
midpoints?
midpoints.
Are they midpoints?
I got a from one of the reviewers of some of my papers, he suggested investigating moving them, which is a good point, but it would sort of introduce unnecessarily complications to something that's working. I also investigated a method which is basically a weight version of B-splines, which are nerves. They're using catalog, but you can sort of add different weights, so it does the same effect of moving the control points. But by adding, they're rational, so adding more weight in here sort of pulls the entire curve, which is sort of against my assumption that we have a local support point. So I can look at each segment by itself. Still working on Sam. Still waiting. Yes.
Just a question on maybe just your comments on the repeatability of data, because there's obviously a random factor.
Mm-hmm.
What are your comments?
On the which
on your approach.
So with randomized planning, there's no certainty. It's always probabilistic. But I used Mole's benchmark, so the number of the population size that he prevented, all the sort of the non-parametric statistical methods that he proposes, also box plot, histograms, the cumulative distribution function, but they're all sort of estimates. They can't be 100% sure. But I go into sort of an analysis in the thesis of the probabilistic completeness of the algorithm. So given infinite amount of time, you'll get a solution. It's just a matter of how difficult or how much time you get that solution.
Maybe just another question. It would be very interesting to compare your proposed method with an actual human. Have you thought about that?
It's been done published in Nature, I think in 1994. Yeah, but they've shown that the way that humans drive, and I've actually been doing this ever since I started just looking at how I'm driving, but humans drive with continuous curvatures. So if you look at yourself doing a lane change, right, and that's sort of the disadvantage of Dubin's method, in which it's just a sudden change. So you wouldn't be doing that when you're driving. And for autonomous cars, we're actually more susceptible to motion sickness because we're not driving, so you don't know where the car is going. So the lateral acceleration has sort of a more complicated effect on you. So you want to minimize the lateral acceleration. Dr. Mohamed?
Just a quick question. I saw that even in your future research, you're suggesting just C-squared continuity.
Mm-hmm.
Is there any specific reason for not going into higher orders, or?
There is. I did like a study between all the orders in terms of how fast you can generate them, because I'm generating them using the recursive formula. So it's sort of a triangle that grows. So when you increase the order, it's not one level of increasing the calculations. You have to do them for all the calculations. So I looked at fourth order curves. Even though they're smoother, they sort of move further away, so that sort of the least square error, or the square error increases when you increase the order results. So what you're gaining in continuity, you're losing in the tracking error and the time to generate that path. Because I'm generating trees of that stuff, so it has to be efficient, even though I'm using
Just a suggestion. I think if this is going to be used for autonomous vehicles,
yeah.
Then you need to be able to consider the acceleration and jerk applied to the passengers as well.
Well, the acceleration is continuous. It's the jerk that's not continuous. But my work, so B-splines are not the main part of my research. It's a solution to generate the path. But it's more general. So for example, you've done work with clothoids for paths. If you can generate that in real time, you can input it to that.
Mine doesn't work in real time.
Yeah, well, that's the problem with clothoids. But if you could, you would generate it. You can generate it using that tree. So it's general for any path that you can generate.
Yes. Slide number, I think, 50. You have
50 or 50?
50. Yes.
50.
This one or the one?
Yeah, that's that one, yes.
Yes.
Might have, yes, good calculus. We have considered the noise for the simulator model.
Yeah, yeah.
How can I say? Considering the effects of the noise. What the noise represents in real world here?
So the noise, when we're looking at had a lot of discussions about this, but what it's modeling, because in the real system I have a belt that's driving the car and it sort of oscillates, and there are from the road. So when I was showing the real experiments, it's not even. So the car is always sort of, even though I don't consider roll in my experiment, it has to roll, especially when it's turning at higher speeds. So that adds also noise to the steering end of those.
The reason I asked is you consider your noise as a normal distribution. So
Yeah.
it's very
So easy.
analysis friendly.
Yeah, exactly.
So, but do you think that is a good assumption for your system?
I use
You have
that.
any data, for example, to look at the distribution and say, okay, this is.
The way that I sort of validated it, because it was matching the resulting accelerations from the field experiments. But the reason I used a noise, because that's the sort of the standard experiment. It's one of the standard experiments that they use for tracking controllers. So I've cited the work that actually uses that approach. But because my research isn't really on the controller, I'm just using standard controllers to evaluate my paths. I just replicated the experiment conditions that they've. So it's also replicated in other research, the national research.
Good, thanks.
Yeah, please.
In your last results, I'm just trying to, you've done contributions along, quite a lot of contributions all the way across the path planning problem. The last results you had with the planning times, yep, these sort of ones, these experiments here. Now, did you do them with the motion planning using the tracking controller and the model of your vehicle as well?
So these ones are just generating.
Okay, so you're just generating paths, not actually looking, including the tracking performance on top of that. So clearance and maintaining path with a practical controller, for example.
No, I haven't looked at that. But the assumption is, again, because I'm not looking at the controller performance. Assumption is this is the planning box. It's done.
Yeah, assuming it can travel it perfectly. Okay,
Yeah,
that was my
exactly.
question. So then that goes back to your study presentation about looking into the safety constraints. And okay, you can generate these beautiful paths very efficiently in a very complex environment. But then when you come to that practical implementation of controller, as you showed, you overshoot a little bit here, and some of those paths aren't actually safe or valid.
Yeah.
No, okay. So that's okay. I was just wondering what the.
But this is looking at the safety from Freshart's perspective, which is minimizing the decision time for the
as opposed to a clearance with a given overshoot or of an obstacle or
between
something like
cars.
that.
And I think that would be the inevitable collision states that I've discussed, which sort of models the motion of the vehicle and expands the vehicle or the other obstacles based on your motion and the other motion.
Are you aware of any multidisciplinary optimization approaches that try and balance those competing objectives? One, minimizing acceleration on the passenger; two, clearance of obstacles; three, time; and four, path length.
There is a paper from the same journal that I published this approach, but it was designed as like a path aid or a driver aid, sort of. So it would recommend when you're driving, it would sort of augment the path that it would recommend for you based on these criteria. In the table that I've shown, there was one that was done for UAVs actually. For some reason I forgot all the paper names.
Is that Felipe?
I think it was
Gonzalez?
Nicholas. He used a genetic algorithm to. I'm using control point. I'm generating control points. He used a genetic algorithm to optimize the positioning of that of the control points based on a fitness function, which is weight based on I think onboard energy, clearance from These just sort of simulated functions with obstacles.
Okay. First of all, I would like to say well done. Well done. Then, it was my pleasure to supervise you. I guess Professor Reza would say the same. You are the student which you were leading your research. We are trying to follow you. You did very well. You just skip most important PowerPoint slides, which you will explain to us right now, and we may wrap up with this. So, PowerPoint 8 in 1.
Other contribution.
Exactly. Most important one, for the record.
You can guess who asked me to add that slide in. So again, I guess to summarize, my contributions are theoretical. We're the first people to look at sampling-based planners, categorize them, and theoretically analyze them. I investigated passenger comfort factors for autonomous vehicles as well. I designed several algorithms for path planning, boundary value planning, and randomized planning. And the experimental are the improvement of pure pursuit and tracking performance and randomized motion planning performance in standard experiments. Cuie.
Any other questions? So I have some questions. Initially, what is your aim in this research?
So my aim is the the main question that I showed in blue, which is improving motion planning for autonomous cars based on the criteria by Dills and Fishard, which is minimizing the decision time and reducing or improving the motion profile instead of disturbances. And I've shown that using simulations and experimental results that I've achieved that method. And I validated that we can use any continuous path to achieve those results within the framework that I proposed.
So the experiments also
Yeah, at RMIT in, I think, in front of Greg's office, the field experiment.
So what are you most proud of?
Most proud of, I think,
Of your findings?
of my findings. It's, I think, there's two things. The randomized planner was published in a very good journal, so I was proud of that. And the pure pursuit improvement as well, that was published in a very good journal, which I wasn't expecting to get in. So these are the two main results. But generally, yes.
Okay, thank you.
Thanks. I was going to say beating great people, but that's what I was proud of.
So you use the opportunities to study, yes? Your paper, how long can you generally finish this? It's just the final.
Yeah, so it's just the final chapter. I think we're estimating about 46 weeks to finalize.
So you will submitting, you will be able to submit your thesis in around 1 month. After
Sorry?
that?
Yes.
After that? What
well,
is your planning?
I think Dr. Milan promised me a great position in this group.
Are you expecting more papers?
Yes. So